Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this lecture, we're going to begin looking at the chemistry of ethers and epoxides. We'll first begin by examining the preparation of ethers. The most common ether, diethyl ether, is formed by the dehydration of ethyl alcohol. It's first reported in the 1500s. The industrial preparation for diethyl ether is a reaction of ethanol with sulfuric acid. H2SO4 at 0 degrees C. The acid actually makes ethyl hydrogen sulfate. And ethyl hydrogen sulfate, when reacted in ethanol at 140 degrees C, converts to diethyl ether. Actually, I'm going to have to Now, how does this reaction proceed? Well, it turns out that ethanol acts as a nucleophile and does an SN2 backside attack on ethyl hydrogen sulfate. Now, even though it's not chiral, I'm going to draw it as if it were, just so we can see the backside attack. And so, we have the good leaving group, HSO4 minus. We do SN2 here. Let's draw the transition state. Just to review. So I have C2, H5, O. There's an H on it. And I have a bond forming. Over here I have O, S, O, 3, H leaving. And I have an H, H, CH3, let's make that CH3 a bit clear. So I have Bond breaking. Bond breaking. Not enough room. I'm going to have to write that out here. So bond breaking. And there should be a double dagger here. I don't have room, but there it is. And we have a bond forming. And now we can just show this oxygen is picking up a positive charge. It's delta plus. And this oxygen is delta minus. So that when we are done, we have C2H5O, then H off of it. It's positively charged. And C2H5 on this side. The leaving group was HSO4 minus. Okay, now the HSO4 minus, or the ethanol, comes in and grabs the base, so minus H plus. So ethanol acts as base, grabs H plus, or the HSO4 minus. And we have diethyl ether. Diethyl ether is one of the most common ethers. Diethyl ether can be prepared in this manner. It is an excellent solvent, and it has a known anesthetic effect. It has been used in the 1800s as an anesthetic, first reported in the 1500s. The vapors are explosive if exposed to a spark, and the anesthetic effect often is accompanied by nausea. It's relatively safe physiologically and is still used in some limited scope. One should note that chloroform also produces the same anesthetic effect. However, chloroform has a narrow safety margin and can cause liver damage. So the ether is a safer anesthetic than chloroform. Now, the anesthetic effect upon the central nervous system is not well established. It's thought that unconsciousness may result from several factors. The first factor is that this unconsciousness may result from changes in the properties of the nerve cell membranes. Changes in the properties of the nerve cell membrane. Alternatively, unconsciousness may result from the suppression of certain enzymatic reactions. And lastly, it may be caused by just simply the solubility of the organic compound in the lipid membrane, in the cell walls. So solubility of the anesthetic in the lipid membrane. Although it's not well established, it's suspected that one of these three is the cause of the anesthetic effect. Now, two modern anesthetics that I expect you to know the names for, that are used in the medical field today are, one is an organic halide, and this molecule is called halothane. And you're responsible for this name. Halothane. Halo ether, halogen-containing ether, is also used as an anesthetic. And this one is referred to as enflurane. Enflurane. The most ideal anesthetic, halothane, has been still used and has some side effects. Enflurane is also used, and sometimes the two are used in conjunction one with the other. Now, a local anesthetic is an anesthetic that blocks nerve impulses locally. This is commonly used in dental work. An example of this would be the molecule novocaine. Now, I expect you to know halothane and enflurane. You must know those. What I'm giving you now is really just for interest's sake. A local anesthetic that was used to kill pain in dentistry was this molecule. I'll put dots for carbons just so you know it's a 6-carbon aromatic ring. It had an ester functional group, and it had a nitrogen, with 2 ethyls off of it. And the lone pair was protonated, so that end became positively charged. And so the counterion was a chloride. This molecule was known as procaine hydrochloride, or novocaine. I do not expect you to know this structure. Novocaine. It was a widely prescribed local anesthetic used in dental clinics. It was known to act by inhibiting nerve impulse transmission by acetylcholine. A more modern version of this local anesthetic is this molecule. has an amide instead of an ester linkage, but it still has the same cationic end. This local anesthetic is referred to as lidocaine. This is a more modern local anesthetic that works in the same manner as novocaine. Both these anesthetics often had a compound called epinephrine or adrenaline added to it to increase heart rate because they are often accompanied by a drop in blood pressure. Again, these work by inhibiting nerve impulse transmission by acetylcholine. So, anesthetic effect in the medical field and the local anesthetic effect found in the dental field. Alright, I expect you to know the structures and names of halothane and enflurane, but novocaine and lidocaine are given for interest's sake. You do not need to know them. Okay, let's move on and examine how ethers can be prepared in the laboratory. The reaction with ethanol to produce ethers is an industrial preparation. But in the laboratory, the ether is often prepared by what is referred to as the Williamson synthesis. The Williamson synthesis is an SN2 reaction on an alkyl halide that's methyl or primary. So we do an SN2 by attacking a methyl or primary alkyl halide. The attacking group, or our nucleophile, is either a phenoxide or alkoxide. I.e., the attacking group is either this type of molecule or an RO minus, where R is some kind of alkyl group. The alkyl R can be methyl, it can be primary, it can be secondary, it can even be tertiary alkoxides here, or allylic, or benzylic. So this reaction works with a wide range of alkoxides. So for example, in the Williamson synthesis, I can take ethoxide anion. Now remember, don't be confused by this. This is the anion. You can't get a bottle of anion. So the ethoxide has some counterion salt. It's found in some salt form. So it's either sodium ethoxide or potassium ethoxide. So don't be scared if I write it this way or I write it or I might not show the lone pairs. I might just put the K right beside it. If I write that, that's just potassium ethoxide, the same thing. K plus, O minus. So don't be surprised if you see a counterion. Now I could react this, for example, with ethyl bromide. This is a powerful nucleophile, a primary alkyl halide. This goes really well, SN2. Goes really smoothly and makes diethyl ether. Very nicely. I can take phenoxide and do the same thing. I can have phenoxide attack methyl iodide. Simple SN2. Okay, this molecule would be named methylphenyl ether. I would also accept phenyl methyl ether. Space between each word, but this methylphenyl ether has an accepted IUPAC name that really came out of its common nomenclature. Just like phenyl with an NH2 is called aniline, this guy had a special name. You learned that name already. This is not aminobenzene. This is aniline. And you already know that. You already had that. Well, this molecule has a special name called anisole. Anisole is methylphenyl ether. Anisole is the preferred and better name. So if you ask to name this, you will not call it methylphenyl ether, but rather you'll call it anisole. Anisole is accepted by IUPAC. Okay, that's how ethers are prepared. What about the reactivity? Well, the great thing about ethers is they have limited reactivity. That's what makes them good solvents. The last thing you want a solvent to do is react with a lot of compounds. If you want to dissolve something and carry out a reaction in the solvent, you don't want the solvent interfering with the reaction. Ethers are great for that because ethers don't do a lot of reactions. Their reactivity is very limited. And there is only one reaction I'm going to give you that ethers follow. Okay? And we're going to look initially at 3 reaction examples and then look at the mechanism. So, If you heat up ethers with hydroiodic or hydrobromic acids, you can get substitution reactions taking place. So these are substitution. Substitution reactions. Of ethers. Okay. Now, suppose I have two alkyl groups, and the alkyl groups don't have to be the same, so I'll call one R and one R prime. And the R prime simply means that you could have ethyl methyl propyl here, you could have ethyl methyl isopropyl here. It doesn't matter. They could be the same, they could be different. If you hit this with hydroiodic acid, and sometimes you'll see the word excess written here, or EX in front of HI. You might see a little EX in brackets, like this, which might mean excess, okay? HI and heat. You can get it to attack and substitute iodines at both carbons. So you get Ri plus R prime I. And if R and R prime with, say, both methyls, you get two methyl iodides. If they were different, you'd get different alkyl iodides. If you attack anisole or some other phenyl ether, and you hit it with HI and heat, the I can come in and attack, but it will not attack the phenyl end. The phenyl end will stay as phenol, but the R end will form your iodide. And lastly, if you use diphenyl ether, with HI and heat, you get no reaction. No reaction. Now, what's interesting about this process is its standard substitution, SN1 or SN2, and we're going to look at that. But before we do, we want to understand why the aromatic ring seems resistant to it. So I'm going to draw an edge-on view of our aromatic ring. Put in the two p orbitals that produce the side-to-side overlaps. And this produces delocalized electron density above and below the plane of the ring. So we also have the same thing down here. So you've got these rings of delocalization, if you like. And inside this Paul cloud of electrons, and you got an O, and say you got some carbon with other substituents off of it. Now the first step, of course, in making any O-bearing, such as alcohol, ether, a good leaving group is protonation. We'll protonate the lone pair, and we'll form a good leaving group. Now here's where the pi cloud comes into play. The nucleophile is I minus. I minus can come in and backside attack this group, or it could leave and give you a carbocation, and then attack. But if I minus tries in any way to attack this carbon, there's this rich pi cloud of electrons here, negatively charged, that repels the nucleophile. And the I minus nucleophile cannot attack this carbon, which it has to. It must attack that carbon or there's no reaction. And when you have two phenyl groups, there's no place for it to attack. The I minus comes in and bounces off the aromatic pi cloud of electrons, which is negatively charged. Like charges repel each other. So when there's these aromatic rings, I minus gets repelled and there's no reaction. But let's look at this case and see if we can explore this mechanism more closely. Now I'm going to draw a flow chart, although we could split this reaction up into multi-steps. And what we're going to do here is we're going to use an asymmetric ether. We're going to use Diethyl Ether. Terbutyl group on one side and a methyl group on the other. And step one in acid is the production of a good leaving group. You see, if the terbutyl group went SN1 and kicked out OCH3 to give you a carbocation, you'd be getting OCH3 minus, powerful base, bad leaving group. If you got backside attack on the methyl, SN2, kicked out terbutoxide, that would be O minus, bad leaving group. We must protonate first. HI will protonate to make a better leaving group. So plus H plus and that gives me the protonated molecule. Now, the protonated molecule, if attacked now by a nucleophile, will eliminate an alcohol as our leaving group. And that will lead to better elimination. The question is, what happens first? Well, we could perhaps envisage the terbutyl forming a carbocation, that is SN1, occurring first. If SN1 occurred first, I would get methanol plus terbutyl carbocation. The methanol is an acid, so it's susceptible to acid attack. Plus H plus. And that would produce this guy. And then I minus could attack. This would be SN2, backside attack. That could be methyl iodide. The carbocation could be attacked by I-. And if it is, you now get terbutyl iodide. Now let's just change colors for a second. What if we didn't start with SN1? What if SN2 occurred first? That is I- attacked. Well, if I- attacked, you'd get methyl iodide, and you get terbutyl alcohol. The next step, of course, would be protonation. Get the good leaving group water. Terbutyls can't go SN2, so it would go SN1. Form carbocation. Trigonoplanar carbocation would form. And then attacked by I-. To make terbutyl iodide. The final products are the same, whether you follow the blue pathway or the black. The only difference is which happened first. In the blue pathway, the SN1 happened first, giving you carbocation, and then terbutyl iodide, and then subsequently SN2 occurred. In the black pathway, SN2 occurred first, and you removed the terbutyl alcohol, and then the terbutyl alcohol got protonated and went to SN1, forming the carbocation intermediate. But that's it. There you have the full reactivity of ethers. Note that if there were two aromatic rings off of the oxygen, that if you had this guy, don't forget this is a common mistake. If there are two aromatic rings, the aromatic rings repel the nucleophile. The pi clouds are not susceptible. These carbons here that I'm dotting cannot be attacked by a nucleophile because the pi cloud repels the attack of the nucleophile. You might say, could it go SN1 and form a aromatic carbocation? Aromatic carbocations are extremely unstable and don't form easily. They're really high energy. So neither the SN1 or SN2 pathways are available. Okay, so diphenyl ether, when reacted this way, gives you no reaction. If you only have one phenyl group, you will get attack at the one end. You'll get attack on this side, and the other product will remain phenol. Make sure you remember that. Okay. Now, what about epoxides? What is the situation for reactivity of epoxides? Well, let's take a look at substitution. Substitution reactions of epoxides. Substitution reactions of epoxides. Now, epoxides are more reactive than other ethers due to ring strain. Remember cyclopropane? Cyclopropane was a strained ring. It had eclipsed hydrogens, lots of torsional strain, and bond angles of 60 degrees of deviation from 109.5 or 49.5 degrees. A lot of angle strain plus torsional strain yielding a huge amount of ring strain. There's a tendency to have that molecule want to pop open. Epoxides are likewise just a strain. The epoxide has a huge amount of ring strain. Now, the reactions, substitution reactions, are typically acid or base catalyzed. That means they go much more easily in acid and base, and actually, depending on the conditions, you get some variation in effects. But simply put, to summarize the reaction, if you have simple epoxide, you can hit it with HCl. You will protonate the oxygen, making an OH. The Cl will attack, breaking that bond, and you will get a CH2 OH. CH2 Cl. Likewise, if you attack it in base, oxygen has 2 lone pairs, say hydroxide, and if I'm using hydroxide as my salt, I always use the conjugate acid as a solvent, so H2O's my solvent. Hydroxide will attack, the alkoxide break off, the O- will grab a proton. Nice way for making a 1,2 diol. Okay. Let's take a close look at the reaction mechanisms. And the mechanisms are slightly different, so we're going to look first at the acid catalyzed, and then the base catalyzed attack. Now the first thing to note is both reaction mechanisms are SN2. The ring strain opens up and exposes more of the carbon. Because the bond angle is only 60 degrees in the ring, whether the ring's heavily substituted or not, you can get SN2 attack. Okay. Let's begin with acid catalyzed. Then to examine what happens, let's use an asymmetric epoxide. Because we're an acid, step 1 will be protonation. So, we have an epoxide, we have a C, and off of that C we're going to have 2 methyl groups. Then over here, just going to have a CH2. So this is 2,2-dimethyl oxyrane. Notice it's 2,2-dimethyl. Why would the name be 2,2-dimethyl oxyrane? The reason is oxygen gets number 1. Heterocyclic rings, heteroatoms are often numbered. In this ring, oxygen's 1, so this carbon's 2. Step 1 is protonation. This is the lone pair. So there's a plus here. We produce an oxonium ion. Now this positive charge is stabilized by inductive electron donation of carbons. So both carbons are pumping in electrons through the sigma bonds to help. And the fact that oxygen's electronegative helps draw those electron density. Oxygen, which is normally electronegative, becomes very electronegative when it's positively charged. Hence, we get a lot of delta pluses on these 2 carbons. Now, step 2 is nucleophilic attack, and we're going to pretend we've used an acid like nitric or sulfuric that has weak nucleophiles. And we're going to do it in ethanol. Or perhaps we use an acetic acid, which has a weak nucleophile, and get our alcohol to act as a nucleophile. So step 3 is nucleophilic attack. We are going SN2, so it's backside attack. Fortunately, I don't have any chirocarbons to worry about. But if there were, I'd simply get inversion. Now, in nucleophilic attack, in this molecule, the inductive electron donation puts delta pluses on the two carbons. Oops, that should be 2. I knew I did something wrong. And because the molecule is asymmetric, the size of the delta plus that actually forms on the two carbons is different. The oxygen actually binds closer to the CH2, and inductive electron donation, if you like, is greater from the carbon with the two methyls. So when the nucleophile is coming in, if it sees a delta plus like this on the CH2, it sees a delta plus like this on the carbon with the two methyls. The larger delta plus is more positive charge, and it draws in the nucleophile, which I said was going to be methanol. It draws in that nucleophile faster than the other carbon. So in acid, we attack the more hindered carbon. So in acid, you attack by SN2 the more hindered, the more substituted or sterically hindered carbon. So in acid, the methanol is going to attack this carbon. That will break this bond. And you will end up with a CH3. Actually, let's put this up here. Now very quickly, the next step is minus H plus. Deprotonation. I don't have room, but this is also step 2, not step 3. Step 3 would be deprotonation, and once you've done that, you would have gotten draw it a little higher if I can. So there's your product. Let's put a box around it. Your final product. If I was to name this, alcohol's the highest priority group. 3 carbon chain. It's a propanol, 1 propanol with a 2-methyl, 2-methoxy. Okay. So 2-methoxy, 2-methyl, 1 propanol. We'll name the products and compare it later. Let's continue now and look at what happens in base. So let's redraw this product. The product we made. From the acid attack. Which was 2-methoxy, methyl, propan, one all. Okay. Let's try the reaction in base now. All right. In base. Now the reaction is still going SN2, but this time there's no acid for the initial protonation step. So let's try methyl, C, methyl, O, CH2, and we're going to attack it, SN2, and we're using base this time. So instead of just methanol and acid, we have methoxide, maybe sodium or potassium methoxide, negatively charged. Use the conjugate acid as your solvent, methanol. Okay, now we have to have a little chat. What's different here? Well, what is different is the oxygen does not have a positive charge. Positively charged oxygen is far more electronegative than oxygen itself. Yes, oxygen's an electronegative atom. Yes, it will withdraw electron density. But the size of the delta pluses it's going to put on these two carbons is much smaller than the delta pluses that the oxygen positive puts on. And because they're both smaller, the size relative charge difference is smaller. That is, I said the tertiary carbon here has more delta plus than the CH2. Well, now the delta pluses are so small, that difference is smaller. Not enough to attract or control where the methoxide attacks. Because of this, normal SN2 steric rules apply. That is, the bulkier carbon is more hindered, and attack therefore occurs at the less hindered CH2. Now, in the acid case, the delta plus was so large that it overcame the steric hindrance, and the delta plus, larger delta plus on the tertiary carbon, more hindered carbon, attracted the nucleophile. In this case, however, the actual methoxide attacks the less hindered carbon. When this happens, of course, this bond will break, and we'll get CH3, C, CH3, O minus, and we'll have a CH2 with an OCH3 off of it. Now, this guy's very basic. He's basic enough that in equilibrium, with lots of methanol around, he will pull a proton off methanol. Now, because methanol is a solvent, once the proton's been pulled off, the methoxide that forms is unlikely to come in and hit it again. There's so much excess methanol around compared to the product molecule that effectively it never gets deprotonated. Because remember, when something's a solvent, it's present in vast excess compared to the molecules dissolved in it. And so here is our product. And we can name this product 1, 2, 3 carbons. This is a propan-2-ol with a 1-methoxy-2-methyl. So we have 1-methoxy, 2-methyl, propan-2-ol. Now, if you look at this molecule and the molecule formed from acid attack, you see clearly that they are different. In acid, you attack the more hindered carbon. You attack the more hindered carbon because positively charged oxygen withdraws electron density asymmetrically. This induces a larger delta plus on the carbon, enough to overcome the steric hindrance and attract the nucleophile at the more hindered carbon. I'll say that again. The electron withdrawing is sufficiently large on the more hindered carbon, and the delta plus formed there so much larger than the CH2 that the attraction to the delta plus is sufficient to overcome the steric hindrance caused by the two methyl groups. And in acid, you attack the more hindered carbon. But in base, oxygen doesn't have the positive charge. Oxygen is less electronegative. The delta pluses are smaller. The difference in the delta pluses is smaller. And here, steric hindrance takes over, and the alkoxide attacks the less hindered carbon. This results in two different products. So we can control which carbon you attack by just changing the conditions, either basic or acidic. All right, let's take an example of a fairly complicated molecule and see how this comes out, and see how we can actually tell that it's SN2. Suppose I had this molecule. And over here was an H. Over here, there was a methyl. And over here, there was an oxygen, which was an epoxide. So it's coming out of the plane. And suppose I attacked it. Two different reagents. The first reagent was H plus and methanol. And I use an acid whose counterions a weaker nucleophile than methanol. So methanol will be our nucleophile. In this case, H plus will protonate, and we will attack the more hindered carbon. No problem. When we attack the more hindered carbon, it comes in the back side. this is coming out, it comes from behind. That means this bond will break and the CH3 will invert because SN2 gives you inversion. The O from the epoxide becomes an OH. The methyl inverts. The methyl gets the wedge. And because it attacked from underneath, the OCH3 gets the dash, and that should be dash bonds. So there you go. The OCH3 attacked from underneath, this CH3 inverted, and this guy, this bond right here broke, and that became your OH. But what if you did it in base? Dissolved in methanol. Well, indeed, SN2 still happens, but base goes for the less hindered carbon. Yeah, let's make this ring bigger so we have more room. There we go. Oops. Okay. This time methoxide attacks the less hindered carbon. This wedge breaks. So down here, the O of the epoxide becomes an OH, and you have the methyl still pointed down. Now when you get backside attack by methoxide, the H will invert and it will get the wedge, because SN2 at chiral centers leads to inversion. And the OCH3 will have come on underneath. So you see, in a complicated epoxide that's chiral, you see both the inversion and the attack either at the more hindered in acid or less hindered in base by the methoxide. Okay. We have one more short section to discuss now before we leave this section, and that is the analogs to the ethers and alcohols when we replace oxygen with sulfur. And they are called thiols. That's the analog to the alcohol. Take an OH and replace the oxygen with an S, and you have an SH group. That's called a thiol. And if you have a thiol ether, replace oxygen in an ether with sulfur, we have what is called a sulfide or thiol ether. So thiols and sulfides. Now the analog to the alcohol is named as an alkane thiol. and you're responsible for this nomenclature. The common name was mercaptan. Mercaptan. The SH group itself is called a thiol group. So that would be like saying a hydroxyl or hydroxy group. And it's sometimes called a sulfhydryl group. So let's try some nomenclature. CH3, CH2, CH2, SH. Okay. This is propan. One thiol, or 1 propane-thiol. It is also called propyl. The common name is propylmercaptan. Okay. Propan 1-thiol, ethane 1-thiol, or ethane thiol. If you had it off the second carbon, this is propan 2-thiol. Propan 2-thiol or isopropyl mercaptan. Okay. The characteristic property of thiol is its odor. Ethane thiol is a key constituent in skunk spray. Very powerful odoriferous compounds. Very strong stench. Now if we compare the simplest analog, H2S, it has a pKa of about 7, whereas H2O, remember, had a pKa of about 15.7. So H2S, which is sometimes referred to as sour gas, is much more acidic. Because of this, thiols, which have pKa somewhere around 8, they are also more acidic than water or alcohols. So they have a tendency to lose their H more easily and become sulfides, S- groups. Also, sulfur is less electronegative than oxygen. And water, you know, has a boiling point. Water has a boiling point of 100 degrees Celsius. This is caused by the strong hydrogen bonding. H2S has a boiling point of minus 61, so it's a gas, degrees C. And H2S's low boiling point is attributable to the far weaker hydrogen bonding because of the lower electronegativity of the sulfur. Now, SH- is a powerful nucleophile. H2S readily dissociates into HS- and H+. And we learned that HS- is one of the most powerful nucleophiles when we learned about nucleophiles in alkyl halide section. And so SH- or HS- can attack a molecule like methyl iodide, do SN2, and produce methane thiol. Plus I-. It is tricky to isolate methane thiol because methane thiol readily ionizes. Producing another very powerful nucleophile. In fact, methane thiol itself is a strong nucleophile, but when it becomes methyl sulfide, this methyl sulfide then could attack another methyl iodide, and you get, if it does this, CH3, the analog to dimethyl ether. You get what is called a dimethyl sulfide. The analogs to ethers that contain sulfur are named sulfides. And here we have dimethyl sulfide. And it'd be named just like ethers. If you had different groups there, you'd have methyl ethyl sulfide. Now, oxidation of thiols can take place to make disulfide linkages. For example, you can take 2 ethane thiols, and if you oxidize them, oxidizing would follow the top arrow. Remember, oxidizing is the removal of hydrogen. Bottom arrow going backwards is reduction. Reduction is the addition of hydrogen. With fairly moderate oxidizing agents, you can produce disulfide linkages and produce molecules like this, which is diethyl disulfide. Now, this type of chemistry is very important because it's the type of chemistry that goes on in hair salons. It is also the chemistry responsible for the differences in human hairstyles. Some humans have very straight hair, and some humans have very curly hair. If you are a very straight-haired person, biochemically, your hair is on the left side of this equation. But if you have naturally curly hair, biochemically, you are on the right-hand side of this equation. There is an amino acid called cysteine, which has an SH group in it. The cysteines of the hair can be oxidized into crosslinks that cause the hairs to bend and curl. And the disulfide linkages in cysteines hold the hair into a curl. Now, as hairstyles change with fads and popularity, curl comes into and moves out of style. And so if you like, at the hair salon, you are actually carrying out chemistry on your head. That is, if you're putting in a perm, they will remove any curls, they'll straighten your hair, they'll put your hair in a curler and apply an oxidizing agent and let it reactivate, permanently create these disulfide linkages. Once removed, the oxidizing reagent is moved and the curl is held into position in what is called the perm. The perming of hair is actually carrying out chemistry on the hair where you oxidize the thiol linkages and produce disulfide bridges. Perms last for varying lengths of time depending on the biochemistry of the individual. As hair grows out and these linkages break, your curl will be lost. Okay, the last thing to note is that we can conduct chemistry on sulfides, such as dimethyl sulfide, in which we oxidize the sulfur by adding varying amounts of oxygen. So if we use peroxide and we do it in acid, at 25 degrees C, we can produce a molecule called dimethyl sulfoxide. Dimethyl sulfoxide. Short form, this is one of the aprotic solvents you had to learn, DMSO. If you carry out this reaction in H plus at 100 degrees Celsius, you'll produce the sulfones. So you have to be careful with regards to reaction conditions. Sulfur likes to get oxidized. You're not responsible for the name of this product, only its formation. I want to spend a little time talking about dimethyl sulfoxide. Dimethyl sulfoxide is a very unique solvent. It's a very unique solvent. It has what is called a high dielectric constant. A high dielectric constant. What does that mean? Well, in simplest terms, a high dielectric constant allows it to insulate charges. Okay? It's able to insulate charged ions from one another. It does not form hydrogen bonds, so it's aprotic. Because of its high dielectric constant, because it's able to insulate charge, it can dissolve both ionic ionic, and organic compounds. That would mean it would allow compounds to react. I could dissolve an organic halide with a sodium hydroxide and allow them to react. And often reactants show enhanced reactivity. Enhanced reactivity. Now, the problem with it as a solvent is very high boiling. Very high boiling point. And it's difficult to remove without decomposing your reagents and products in the solution. It's approximately 189 degrees Celsius. So this is really the drawback to it as a solvent. Now, dimethyl sulfoxide has some other interesting properties. First off, it's readily absorbed through the skin. In many ways, it will carry anything dissolved in it right through your skin into your bloodstream. To some people, it represents a solution to the hypodermic needle. That is, we would not need to use needles if we dissolved our compounds in dimethyl sulfoxide and allowed them to be injected utilizing DMSO. One of the side problems is it leaves a terrible taste in your mouth, and I mean really terrible. Also, the toxicity, has not been well researched. There's been insufficient testing. However, there are no known significant toxic effects. Another side effect is DMSO's ability to instantly kill pain. This has been used in horse racing and has even been used, although banned, in the NFL. If a football player or horse damaged its leg, you could put DMSO on and it could go out and run again. However, in the case of a football player, if his knee was damaged and he went out and played on it, he could permanently, seriously damage the knee. And as such, removing pain is not always a good idea. So dimethyl sulfoxide is not just an aprotic solvent. It has many interesting properties. Okay, well that's it. And this brings to a close our section on alcohols, ethers, epoxides, sulfides, and thiols. Next lecture we'll be pressing on introducing alkene-alkyne chemistry. My name is Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.